Okay, hi y'all. Let me share my screen so that we can see my dot cam and get going. All right, so picking up where we sort of left off, that's much better. So vertical asymptotes, zoom in here, hide that little thing. Remember we talked about for part C, we need to be in lowest terms. And the vertical asymptotes come from whatever makes the denominator 0. So for example, for A, taking the denominator, setting it equal to 0, we see that 1 makes that 0. So we have a vertical asymptote at x equaling 1. B, same thing. We want to take the denominator, set it to 0. Factor, let's see, 36 is 6 times 6, but also what? 3 and 9, 3 and 9, but that's not a difference of 5. Let's see. 36. 36 and 1. 2 and what's that? 18? Yes. 3 and 12. 6 and 6. And then let's see. 3 times, why am I blanking on this? Oh yeah, 3 times 9 is 27. 4 times 9, here we go. 4 times 9 is what I need. I couldn't get my fingers to work, right? Put my fourth one down, that's 36. There we go, brain, get it together. This is why I like being in class. You guys can just shout the answers at me and I don't have to think so hard. Okay, so I need 9 to be positive, 4 to be negative, because 4 and 9 need to multiply to a negative 36. But 9 minus 4 needs to add to 5. So from here, the zero product principle, by taking each of these factors, setting it equal to 0 and solve, say that x equals 4 and negative 9. So here are our vertical asymptotes. So we have vertical asymptotes at x equaling 4 and negative 9. So on a graph, if let's say here's 4, here's negative 9, we would just represent them with these dotted vertical lines. Same thing would happen here. This is 1 represented by a dotted vertical line because technically it's invisible. We did see in class, but remember that you need to make sure that it is in lowest terms, right? So here, the only vertical asymptote is at x equaling negative 4. There's a hole at x equaling 4. So this graph, if I draw it for you, let's call this 4. Here's my vertical asymptote. Oh, here's my vertical asymptote. Here's 4. You literally have a hole in the graph. Okay. Oops, sorry, I need to come over that way. There we go. Here, again, set the denominator equal to 0. We see that x squared equals negative 9, but then we're done because no squared number equals a negative. So this has no vertical asymptotes, right? DNE does not exist. Perfect. This one will get you. Okay, this one I like to put on test because if you're paying attention, it's super easy. But just remember, vertical asymptotes come from where the equation is in lowest terms. The domain just comes from the original equation. So the domain for this equation would be all values of x such that x does not equal negative or positive 4. Keep in mind there's only a vertical asymptote at negative 4 because 4 has the hole because these two terms canceled out, right? They like went into the cloud, so to speak. Like the information is there, it's just no longer like on your computer, it's in the cloud. If that makes sense. It's a hole in the graph because it reduced out. It went away. Okay, horizontal asymptote, or thought of as in behavior. In behavior. Oops, for rationals. Okay. If the line y equaling d is the horizontal asymptote of the graph of the function f of x, if f of x approaches d as x approaches positive or negative infinity, okay, then we have this. Okay, so this just says as x goes way, 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 way right, as x goes way, 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 way left. Okay, so what is happening at the end? What is happening at the end? So if this is my graph, what's happening way, way, way over here on the right? What's happening way, 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 way over here on the left? We don't really care what's going on in the middle. It can just be, do its thing. Okay. All right. So here, given the rational function, if you look at the leading terms, ax to the n over bx to the m, here you're basically evaluating the ratio of the degrees. Okay, you're evaluating the ratio of the degrees. We have if you are top heavy or bottom heavy, if they're equal, or if it's what I call bottom heavy. Okay, let's see. So here I call this bottom heavy. It is also what we call proper fraction. Proper. These are both improper. All right, here they're equal. This is what I call top heavy. Here are different examples. So, well, let me talk about the definition. Hello. So if I'm bottom heavy, then the asymptote is y equals 0. If they equal, then it's just the ratio of the leading coefficients. If you're top heavy, then there's no horizontal asymptote. Okay, there just isn't one. Okay, maybe your favorite rule. There just isn't one. However, if the top is heavy by exactly one more than the bottom, then we have what we call a slant asymptote, which is the quotient when you divide the numerator by the denominator. Okay, so what the heck does that mean? So if the degree of my numerator is equal to the degree of the denominator plus 1, so I'm top heavy by exactly 1, then we have the slant asymptote. Then we use long or synthetic division of the polynomials to find said slant asymptote. It's of the form y equals mx plus b. Because you have this 1 degree difference, it'll always be linear in nature. Okay, your slant asymptotes are always y equals mx plus b. Okay, it's always going to be a degree of slant. So here's some examples. I'm looking at my degrees. So here I have a 2 over a 3. This is bottom heavy. So the horizontal asymptote is y equals 0. Now, why is that? Why is that? Well, if you think about it in terms of, well, an example, let me get my different color. If I have 1 over 1, 1 over 2, 1 over 3, 1 over 4, notice that here I'm just 1 all the time because x squared over x cubed can reduce down to just 1 over x if you would. 1 over 5, and then let's say 1 over 100, 1 over 10,000. Well, notice as your denominator gets bigger, 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 your overall decimal, right, gets smaller and smaller. I have 1, 1/2, point through repeating. Oops, 0.25, 0.2, and then 0.01, and 0.10 hundred thousand, 10,000. Notice that your decimal is getting closer and closer and closer to 0. So this is why if you are bottom heavy, your horizontal asymptote is the line y equaling 0, because your numerator is going to be relatively small comparative to your denominator, which is going to get big, 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 big. Now here, change colors. Again, we want leading terms, so make sure that you're looking at the right term. Here, the degrees are both 2. 2 equals 2, so we go by the rule that the horizontal asymptote is the ratio of the leading coefficient. So this is just 2/3. Oh, hello, y. Y equals 2/3. Okay. These are kind of boring. They're just definitions. I know, I don't really have any like fancy things to tell you. Okay, so now C. Here, the degree of the numerator is equal to 2. The degree of the denominator is equal to 1. It's invisible, but there. So we know 2 is greater than 1. So this is top heavy. So there is no horizontal asymptote, and that's it. You just walk away. That's it. You just walk away. Let's do this example though. So 2 is equal to 1 plus 1. So we have a slant asymptote. Woo! So we do division to find out what it is. Lucky for us, we can do synthetic division. So I have a 1 on the outside, and then 1, -3, and a 5. Remember, we carry down the first one to get the ball rolling. 1 times 1 is 1. Add down, -2. 1 times -2 is -2. Add down, that's 3. Recall, this is your x squared, your x, and your x, your 0, your coefficient, constant. So here's your x, here's your constant, and then this is the remainder. So my slant asymptote is y equals x minus 2. Because yes, I know the quotient is x minus 2 plus 3 over x minus 1. But when I'm talking about the end behavior, like x might be a trillion, okay? This is so negligible that you ignore it, okay? Because if I have 3 divided by a trillion, that's so close to 0, right? That's a trillion minus 1 zeros before you even hit the 3, okay? It's so small that you ignore it. So you're just looking at this slant asymptote right here. So if I graph it, y equals, let's see, I'll do the fancy fraction thing. Just old school, over to fraction, enter x squared minus 3x plus 5 over x squared minus 3 over x minus 1. And then let's zoom 6. Zoom 6 just gives me a standard 10 by 10 window. Perfect. Notice right here, here is our vertical asymptote at x equaling 1, and here's our slant asymptote. So now if I graph it, x minus 2, see that? Yay! So asymptotes are also the invisible lines that our function mirror, okay, or not mirror, excuse me, guidelines. There are invisible guidelines. That's why they also are very beneficial. Okay, so that's horizontal asymptote. Woohoo! So graphing them, I can grab it. We want to graph them by finding any x and y intercept. Okay, the homework might call them horizontal and vertical intercepts. Just be aware of that. That's super weird and I hate it. Find the vertical asymptotes, find horizontal or slant asymptotes, and then plot at least one point between and beyond each x-intercept and vertical asymptote, then finish the graph. So here, it doesn't really matter what order you find this stuff, but we'll just start with 1. So remember x-intercept, y is equal to 0 forever and always. So the x-intercepts also come from the numerator. That's because when I have 0 equals 2x plus 3 over x minus 4, when you multiply the denominator over, well, anything times 0 is still 0, so you inevitably will always end up with the numerator equaling 0. Fun fact. So minus 3 divided by 2 says negative 3/2 is equal to our x-intercept. Our y-intercept, remember that's x equals 0 forever and always. This says y equals 2 times 0 plus 3 over 0 minus 4, which, oops, excuse me. Oh, 4, hello. I can write a 4, I promise. I can write 4. There we go. Which is just 3/4. Okay, so I have an x-intercept of negative 3/2, a y-intercept of 3/4. So now, if we do the vertical asymptote, remember that comes from the denominator? From denominator. That's x minus 4 equaling 0, so x equaling 4 is our vertical asymptote. The horizontal asymptote, remember, comes from the ratio of the coefficients. So if the equation is y equals 2x plus 3 over x minus 4, you have an invisible 1 and an invisible 1 for the degrees, so they're the same. So you take the ratio of the leading coefficient. And again, I'm sorry, that's just the definition you will have to put on your note card or no. So our horizontal asymptote is y equaling 2, because you have 2 over 1. Okay, so now plot at least one point between and beyond each x-intercept and vertical asymptote, then finish the graph. Let's just start by plopping down some axes and marking our important spots. Okay, x-intercept, okay, here's -1, -2, -3, -1, -2, -3, 1, a 2, a 3, a 1, 2, 3, 1, 2, 3. Why I'm doing threes, who knows? 3, 3, 3, 1, 2, 1, 2, -1, -2. There we go. All right, so now, -3/2, that's -1.5. 3/4 is nearly 1, that's 75.75, so there we go. Vertical asymptote at x equaling 4. Oh, I gotta stop a 4 on there. So I need more room over here. And horizontal asymptote at y equaling 2. Oh gosh, I made this way too big. That's okay though. All right. 4 horizontal asymptote at 2. Why does this feel funny to me? Sorry, hang on, y'all. Just bear with me for a hot second. Keep it going. Sorry. I'm just checking my math. I'm just looking because this feels weird. Um, my y-intercept. Oh, duh. Hello. Y'all were screaming at me this whole time. My y-intercept isn't positive 3/4. It's negative 3/4. No wonder. Hello. Y'all are screaming y'all are just screaming at me. I'm so sorry. Again, this is why I hate videos. I'd rather be in person. All right, this makes more sense. So now, 1 point beyond an x-intercept. So let's say what is f of, I don't know, -3 fit suit y'all? Suits me. I mean, it doesn't matter. 2 times -3 plus 3 over -3 minus 4. That is what? -7 in the denominator. -6 plus 3 is -3. So that is a positive 3/7. What is 3/7 as a decimal? Um, again, I feel like that's weird. Let's just go to the table. Okay, -7 is 1. Let's just expand. -7, there we go. 1. Nice. So I know this boomerang kind of looks like this. Because again, like I said, your asymptotes are also your guideline. Like I should have done it much smaller. Bloop, 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 bloop. Looks like this. There we go. And not so many uncertain terms. So now if I do, say, I don't know, let's see, past the vertical asymptote. 4 is an error. Notice that. 5 is 13. So 5, that'd be way up here at 13. And that's because you have this boomerang shape right here. Oops, sorry, if you want to see the graph. There we go. Because here is x equaling 4. Here's our horizontal asymptote. If I pop it in here, y equaling 2. Notice that our boomerangs have the horizontal asymptote as our guideline. Yippee! Good job, y'all. Okay, we're going to keep going. Next, one more to graph, and then we'll call it good with rational functions. Okay, so x-intercept. Actually pause and then do all of this by yourself and come back. Okay, maybe you paused, maybe you didn't. I hope you really did. But if not, x-intercept. That's y equaling 0. So remember, that's just the numerator. Oops, gosh, see, I almost wrote a 4. This is why I need you. I miss y'all when we're not in class. I really do. Not just for your brains, but also, your personality. So I have an x-intercept at 2. My y-intercept, remember that the x equaling 0 forever and always. Y equals 0 minus 2 over 0 minus, 0 minus 10. So this is -2 over -10, or a positive 1/5. Nice. Okay, so here, just while we're at it, the domain. Remember, domain means you take the denominator and you want to find where the denominator is 0. So 10 is 5 and 2. That's a negative and a plus because I need, oops, sorry, let me scooch. The 2 times -5 is -10. -5 plus. So the reason why I did this, I had a hunch. If y equals, oh no, yeah, okay, we're good. X minus 2 over x plus 2, x minus 5. No, we're okay. We're okay. Sorry. I was thinking it was not in lowest terms, but we are in lowest terms, so we're good. So then the vertical asymptote occurs wherever the denominator is equal to 0. We have vertical asymptotes at x equaling -2 and +5. Our horizontal asymptotes Where that is the ratio of the leading coefficient. So that means we're looking at these two terms. We are what I call degree bottom heavy. Again, this is just a rule. Whenever it's degree bottom heavy, the y equaling 0 is our horizontal asymptote. So now let's plop all of this stuff on here. Look, I'm going to cheat and look to see what the graph looks like on my calculator so that I can draw you a pretty graph. Because that last one, oof, I mean, not my favorite. So now I want to be in charge of getting those a pretty graph. A pretty graph. Sorry, bear with me. I know this is like so thrilling for you. You just can't hold it in. Ooh, yeah, so fun. Okay, again, it's really fun when we have two vertical asymptotes because you get some like loops in there. Okay, let's see. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Why I'm doing 6 of 9, who knows? It just feels right. It really doesn't matter. That's just what I wanted to do, okay? So x-intercept of 2, y-intercept of positive 1/5, that's 20% or 0.2. We'll just plop that sucker there. It's just a sketch. Horizontal asymptote of y equaling 0. Vertical asymptote at -2 and 5, right here. So here's -2. And we're represented by our dashed lines. 1, 2, 3, 4, 5. You know, like the sound effects. Sorry. All right, so now, generally speaking, we know kind of on the ends we're gonna have some boomerangs. Here in the middle, things can happen, but usually you have, like on the ends, you have these kind of boomerang shapes, generally speaking, right? Because again, your asymptotes are your guidelines. In the middle, you might have some kind of swoop like this. We just have to determine what swoop we got here. Since I have my y-intercept to the left of my x-intercept, I'm guessing a swoop more like this. But let's just pick some points so that we know what's happening. So let's say we do, I don't know what feels right. F of, that's -2, maybe -4, I don't know. F of -1. Let's say F of 3, F of, I don't know, 7. These are random points, honestly, that I'm doing. That means you pop these numbers into the equation. But I already have it into my calculator. So again, for sake of time, we're just going to use the table. So F of -4 is -1/3. -3 repeating is a -1/3. F of -1 is 0.5, so that's a half. So -4, 1, 2, 3, 4 is a -1/3. We'll call it there. Oh, so that means I know my boomerang is under. I know that we are purely under the x-axis because remember, this is the only x-intercept that we have. It's the only x-intercept we have. -1 is a half, so we're slightly above our 1/4, or excuse me, our 20%. 3, F of 3 is -1/10. Okay, so it's like bloop. Okay, so this tells me I have this elongated, I don't know what you, inverted F, whoop, whatever you want. That's what we got. And then F of 3, oh yeah, that was -1/10 or -0.1. F of 7, notice 5 says error. Can you see that? Because that's where asymptote is. Notice -2 says error because that's where an asymptote is. 7 is 0.27. I don't know what that decimal is off the top of my head. Forgive me. A little more than a quarter. So up here. So 7 up here. So I know we have this decreasing boomerang. Again, I know we are strictly above the x-axis because we only have this x-intercept. In order to go from above to below, we would have to have had an x-intercept here. Same reasoning for over here, okay? Again, I know we have these boomerang shapes because our horizontal and vertical asymptotes are the graph guidelines. So these extra points just let you figure out, okay, where's my boomerang going? So we have two decreasing boomerangs and a decreasing swoop here in the middle. Isn't that kind of cool? This whole thing is decreasing, even though we are not, we are constant, or yeah, constant only on the domain, right? Left to right, decreasing, decreasing, decreasing. That was a lot. I know that was a lot. You're learning. If you have questions, come find me in office hours. Okay, so that is that for rational functions. Now, let's see if I can figure out how to stop recording. Just give me a second. Here we go. Okay, bye. Oh, sorry.